let's get started. Thanks everyone for joining us. I like to start off talks like this with this particular paraphrasing. Some of you have probably heard of Arthur C. Clarke and have heard of his 3 laws before. His most famous of his 3 laws was any sufficiently complex technology is indistinguishable from magic. I like to paraphrase that because I think really the intent here should be focusing on what we learn and digging into learning things better. So in that spirit of not wanting to leave things unlearned so that they are essentially magic to us, we want to dig into those. And there's an awful lot of that happening in this space around asynchronous programming. So today's discussion, we're going to quickly go through some new-ish things on promises and generators. We'll look a little bit at reactive, and our main course that we want to spend some time on is talking about CSP, which is another pattern that most of you probably haven't heard much about in asynchronous programming. Before I even get into that, I just want everyone to know that the purpose of today is to give you hooks into things that I would encourage you to go and learn more about. So I'm not saying that there's any one thing that's like, oh, this is amazing and everything else sucks. There's no way to say it's all one or the other. It's actually a bunch of different bits that we need to learn, different tools that we need to learn how to use effectively. So the goal here is to kind of get you aware of those different tools and help you to see those better. So today I'm going to give a talk that I'm calling Blocking Across the Wire, which sounds a little strange, and it won't be until the end of the talk why you even understand why I came up with that title, but I promise we'll get there. Just a little bit about myself for those of you who may not know. As my name is Kyle Simpson, and I've written a series of books on JavaScript. The book series is called You Don't Know JS. That's not an insult, it's an observation that I am included in of never really actually fully knowing anything and trying to strive to learn it better. So in that same spirit, as I said a moment ago, the whole 6-book, 1,100-page series is available for free online. If you go to youdon'tknowjs.com, it redirects to the GitHub repo. You can also purchase those books professionally edited through O'Reilly and other booksellers. As mentioned in the intro, pardon for my coughing, as mentioned in the intro, I am the head of curriculum for MakerSquare. MakerSquare is an online, an in-person engineering, software engineering school. We train students on how to become better software engineers. We have campuses in Austin, Texas, San Francisco, and Los Angeles, possibly expanding even more to other places. If you're interested at all in that sort of thing, if you've wondered about tech schools or quote-unquote boot camps or things like that, I would love to hear more about it. So if you are interested, definitely reach out and we can chat more about that. All right, let's jump in. Where we're going to start is talking about a topic called concurrency. Now, concurrency is certainly an overloaded term. If you think about all the different ways that that is used, even within computer science, there are lots of different ways that you can get definitions for that, and you could read a Wikipedia article, and that would differ from what you read in a textbook, and that might differ from what is written in a book or in a blog post. Lots of different people have perspectives on what concurrency is. So I'm going to sort of broadly define this term concurrency to suggest the idea is 2 or more things happening in the same time frame. And when I say that, it may sound like what I'm saying is that 2 or more things are happening at the same time, and there's a little bit of a nuance here where that's not exactly the case. So we want to actually dig in. And where this applies to JavaScript, the word that's often used for JavaScript is async or asynchronous. You've probably heard that before. JavaScript is asynchronous. We know about things like set timeouts and AJAX callbacks and event handlers, and we call that async. But what exactly does that mean, and how does that relate to concurrency? Well, it turns out async or asynchronicity, or asynchrony as I like to shorten it, asynchrony is a subtopic underneath concurrency. Asynchrony is a way of implementing, or it is a model for implementing concurrency. Certainly not the only one, but is a model for that. And asynchrony is built in, it's an intrinsic characteristic of the JavaScript language. We have blocking statements that we do, but whenever we step outside of JavaScript to have any sort of communication with the outside world, generally speaking, we step into that asynchronous world. And when I say it's intrinsic to the language, what I mean by that is the notion of functions as callbacks, functions as first-class citizens. That is our hook for asynchrony, and we call that the event loop, which we'll get to more in just a moment. JavaScript is single-threaded. Many of you have probably heard that before. Single-threaded JavaScript means that at any given instant, only one line or indeed one function in your JavaScript code will ever be running at exactly that instant. So we don't have to worry about reentrancy. We don't have to worry about one piece of code preemptively interrupting another piece of code, which is nice. It makes our code simpler. Not perfectly simple, but simpler to reason about when we don't have to worry that this particular statement might be interrupted halfway through. And of course, our friends in the multi-threading world will know that multi-threading does have all of that. There is this preemptive thing. So I mentioned the event loop. What does that mean? Well, in JavaScript, the way this single threading is managed is that we don't want to wait for a long-running task to finish and before going on to the next thing. So each task is basically puts a hook into the event loop and says, I need you to fire this. So when there's a response that comes back from an AJAX request, for example, or when the page needs to repaint itself because you've scrolled, or when there's some update that's come from a web worker, or any of a dozen other ways, whenever there's some sort of asynchronous event that needs to happen, they put a hook into the event loop. And it's basically like waiting in line to get into an amusement park, to get onto a roller coaster ride, and there's only one person that gets to ride the ride at any given time. So nobody gets to cut, nobody gets to say, I'm going to get off the ride and get right back in at the beginning. That doesn't happen. Instead, everybody gets in at the back of the line. So if there are a bunch of those things building up, if the garbage collector and the CSS style repainter and your JavaScript and all these other things are all trying to happen, they're all happening on a single thread. And what we have in an event loop, you can think of it in your mind as basically just a big running while true loop. It's running constantly in the background, waiting for some item in that task list to come up ready to go. It will fire the first one on the event loop, and then it'll move on if there's anything else in the list, and it just waits. And when one task adds another one to the list, then it performs that one next. So you can think of that as just a spinning while true loop that can only do one thing at a time. Which means if I'm currently processing one AJAX response and another AJAX response comes back, it doesn't interrupt what I'm doing. It gets at the back of the line and it waits in the event loop. That's nice because I don't have to worry about my processing right now of this particular response being interrupted by the response to another one. Now, we do still in asynchrony have fundamentally this notion of race conditions, which is if I fired off 3 different requests, and I'm not sure what order those responses are going to come back in, there is a race condition of sorts between those. A race condition is usually a term referring to a negative thing. It's a bad thing, it's a bug in your program. I'd encourage you to actually think about race conditions. They can either be intentional and they can be okay, or they can be bad things, they can be bugs in your program. What changes is whether or not you need to coordinate the responses. So it's not terribly difficult at all to fire off multiple asynchronous operations. We can fire off requests for AJAX and database requests and web worker messages and iframe post messages. We can fire off all of that stuff, just kind of bam, 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 and that's very easy. That's not the hard part. The hard part of asynchronous programming, especially in JavaScript, is getting the coordination correct on the return, on the response to these different events. Coordinating those things can be as simple as I don't care what order they happen in. They really are truly independent, in which case there's no coordination necessary. And that's what I mean by saying race conditions fundamentally are not evil. A race condition can be a good thing or can be an expected or okay thing. For example, you might have 2 completely independent JavaScript libraries that need to load in your page. You put script tags there or you load them with a module loader. You don't care what order those come back in because they're completely independent. There's a race condition there. They are going to add themselves, for example, to the global scope into their own respective namespaces, but because there's no overlap, there's no coordination necessary, and therefore it's an okay race condition. If, on the other hand, you have jQuery and a jQuery plugin that are both loading at the same time, there is coordination necessary because in the race condition, we need to make sure that jQuery itself runs before the plugin tries to attach itself to jQuery. So it's the coordination that's really the problem, and I want to help you visualize the event loop in this way, thinking about how these things interleave and where the coordination comes from. So on the left we have this orangish yellow color with 1, 2, 3, 4. That orange color represents a macro level, high level task like making an AJAX request and response. And on the right hand side we have a bluish green color that represents, let's say, repainting refreshing a repaint of a page after a scroll event. The numbers represent a breakdown into individual atomic microtasks, I'll use them. I'm making up these terms, macro and micro, but what I want to talk about is in multi-threaded programming, it is the fact that these micro level tasks can happen at exactly the same time. That's what people mean by parallelism, that number one and number one could literally be happening in an exact moment. But because we're in a single-threaded world in JavaScript, that cannot happen. The one and the one could be the same, cannot happen at exactly the same time. But we are in a concurrent system. JavaScript's model for concurrency is the event loop. It's the asynchronous event loop. So what does concurrency mean here? Well, recall that my definition for concurrency is that two or more things are happening in the same time frame. We need to understand what things am I talking about. When I say that, I'm talking about macro level tasks. And when I say in the same time frame, I don't mean at any given instant, I mean within a small section of time. So to keep the math simple here, let's imagine that each one of these micro level tasks, each one of these numbers, would take an entire second to process by the computer. We know they can't happen in parallel. They're going to happen in some sort of sequence, one right after the other. So we could schedule this program, we could coordinate this program such that all the orange color ones go first and then all the blue color ones go. That's one way of scheduling this program out. Now, if that were the case, if we fired off an AJAX request and we could not refresh the scroll of a page for that full 4 seconds, the experience of the system would be that it is very slow. It would feel very slow, because it would seem like, why do I have to wait to repaint the page while all these other steps are happening? So that is why we try to do asynchronous programming in JavaScript, concurrent programming in JavaScript, which is that we'd actually like to order these things. We'd like to interleave them. So for example, this is one possible way of interleaving those scripts, and you'll notice that in the same time frame, they appear to be happening at the same time. It appears that while an AJAX request and response cycle is going, we're also taking the steps to repaint the page. Now, in both scenarios, it will take a full 7 seconds to complete all of the work, but the perception of this system is that this system goes quote-unquote faster, and the reason for that perception difference is because of the interleaving of those micro-level tasks. Clearly, the more that we can break down big-level, macro-level tasks into smaller, non-blocking micro-level tasks, the more easily we can schedule these things so that they interleave, and our system will appear more and more concurrent and therefore more and more performant. It's also true that if 2 fires off some other external system call, like a database call, for example, if the orange number 2 requires a database call, we don't want to wait around for a long-running number 2. We want a small number 2 to fire off, and it represents the difference in time between the orange 2 and the orange 3 is that in the background, outside of our JavaScript thread, the database processing is happening. We didn't want to wait for 2 and 3 and the orange to finish before going on, so we allowed that background work to happen outside of the system, while our JavaScript system, the event loop here, continued to be responsive, continued to do other work. That is the essence of writing highly performant and efficient, and the performance is actually more of a perception issue even than an actual scientific issue. But the perception as well as the fact is that the system will run more efficiently if we can do this. The more that we break these pieces up, the more we will run into that coordination problem, which is why I said concurrency is really all about the coordination. So in a parallel system, all of those things would be happening, but we don't have threads, and we are going to coordinate instead in the concurrency model. We are actually going to talk about threads later, which is going to kind of change things a little bit, but for right now, we're just going to assume this notion of our JavaScript is going to happen on a single thread. All right, so let's do a quick kind of review here of some of the mechanisms that we have available to us to do this coordination. The first, most basic, most intrinsic to the language, been around since basically the beginning of JavaScript, is the notion of wrapping up some behavior into a function that we call a callback. It's referred to as a callback because we are going to put a hook into the JavaScript engine that says, whenever you're ready, I need you to call back into my code, and this is the place that you call back into my code. But I like to think of our function as wrapping up the rest of our code. So if you thought about the first half of our program as being the stuff that happens now, and the second half of our program as being everything that's inside of our callback, you can see that there's a split between what happens now and what happens quote-unquote later. That later could be a millisecond, it could be a second, it could be 10 years. We don't care, we just know that there's going to be some conceptual break between what's happening now and what happens later. So we wrap up our program, or part of our program, into a function callback. And the reason we do this is, what I'm contending, is that this is all about coordination. What we're expressing here is that the request called getMore that you see here on line 3 cannot start until after the response from the getData from line 2 finishes. There is a temporal dependency here. We need the data back from the call on line 2 before we can make the call on line 3. And the only way to express that with callbacks alone is to do this, fundamentally do some sort of notion of chaining these functions together through nesting. There are other more exotic techniques like trampolining, where you stick them in an array and pop them off of a queue or whatever, but fundamentally it breaks down to this idea of nesting our callbacks, not visually, but in a temporal dependency. So the inner function that's declared on line 3 cannot run until after the getMore calls back, which is what delays our console.log for not only the getMore call to finish, but that one didn't even start until after the getData finished. So you can see we have a series of steps here. Now, oftentimes this is referred to as callback hell when you start to get the nesting of functions. It has a very pyramidal shape to it, and it seems sometimes referred to as the pyramid of doom or callback hell. I would suggest to you that callback hell is actually about something much more deep than the nesting or indentation. In fact, it has almost nothing to do with that. As I said, you can rearrange this and use other exotic techniques like trampolining and things like that, and then you don't appear to have any nesting at all, but you absolutely still have callback hell. I've written a lot about that, so I won't get too much more into it. But callback hell is about lack of trustability and a lack of sequential reasoning. It's got really very little, almost nothing to do with the visual aspect here. But we chain these functions together because fundamentally, again, we're trying to coordinate the responses to things that have been happening asynchronously, aka concurrently. Now, fortunately, we've grown some new primitives in the language to help make this a little bit easier to reason about, to address some of these problems. The first one that probably most of you have heard of by now is promises. So I've reorganized this program such that instead of passing a callback into a callback into a callback into a callback, I instead have organized it into essentially a vertical chain that will sequentially step through that chain, and it may block at one part of that chain and wait to go on to the next step until it's complete. So line 2 we're going to call getData, and the function that's listed there in the then callback on line 3, that will not finish, or that will not even start until after the promise that came back from line 2 finishes. So the getData function, you'll notice that it doesn't receive a callback, instead it returns as a promise, and we chain off of that promise on line 3. And then you'll notice that on line 4, I call getMore, that one also returns a promise, and because we return it from the success handler of a previous promise, those two automatically chain together, those two promises automatically chain together magically, and that's what makes the line 6 wait for the getMore on line 4 to finish. So now we have this vertical sequencing of things, and we are still fundamentally coordinating our concurrency. Promises are great. I could say a whole lot more about them. I've given a number of talks and written about them extensively in depth. Let me just say this. Since I'm not going to spend too much more time on promises, I don't want to leave you without anything. Let me just give you one takeaway on the topic of promises. There's an awful lot of back and forth among some members of the community. Some people think promises are the best thing that's been invented since sliced bread. Other people think promises are completely meh, and they don't carry any value at all. I believe that the people who don't understand the value of promises are are really not looking at the right thing. I think there's an awful lot of people that have focused on the API aspect of the promises, that there's a .then method and a .catch and a promise.race and all these other sorts of things that has something to do with the API. And I would say that it has nothing to do with the API. In fact, the API that they invented is actually kind of terrible. I'm not all that excited about it. And in fact, I don't organize my code into promise chains like this. I did at the very beginning when I first saw them. I was like, oh, that's super cool and super interesting. But actually, it's not all that interesting. The interesting part, the fundamental paradigm-changing part about promises is that they resolve in a very, I think, graceful way what is called inversion of control. Again, I've written a lot more about that. But that's what promises are really about. They're about restoring trustability to our concurrency coordination, where that trustability does not exist with callbacks alone. And the promise system gives us that trustability. It gives us auditability to know that when we ask for something to happen once and only once and at a specific time, we know that it for sure will happen. So that's really what promises are all about, but I won't get too much more into that here. I said that callback hell was about the trustability thing, and promises solve that, but there's another part of callback hell, which is that it tends to create this non-local, non-sequential reasoning thing. It's our asynchronous code is kind of spidered all across our code base, and you have to jump around, and it's very difficult to follow. In fact, I don't think most developers can ever fully understand all the asynchronous steps in their programs when they're organized around callbacks. We go through enormous lengths, and we've created all kinds of crazy frameworks to try to address some of those shortcomings, but at the end of the day, the fact is that we cannot write our asynchronous code in a synchronous-looking fashion. That is, I think, one of the two pillars of callback hell, is that it lacks the expressivity to do that, which is why this next thing that I'm talking about is so important. Synchronous-looking async is an incredibly important technique, and callbacks alone don't allow us to do that, but thankfully ES6 grew another primitive that helps us, and it's called the generator. The generator is fundamentally about, or its most important thing is it about allowing us to express asynchronous code in a synchronous-looking fashion. And you're going to wonder why that is so important. Why would I say that's so fundamental and so groundbreaking? It's because we continually have to write more and more sophisticated asynchronous code, and it's grown beyond our mental capacities. I'm not trying to insult anyone, but it's grown beyond all our collective capacities to reason about, beyond 2, 3, maybe 4 steps deep in that. And that doesn't even account for when there's forking and all kinds of things like that. We need help. We need better patterns and better tools, and the pattern of generator plus promises is a much better way, I think. So what I'm illustrating here is the idea that that same series of steps that we were first nesting in callbacks and then nesting into a promise chain, we can have that same code expressed in the generator. And what we have written here is synchronous-looking asynchronous code. And there is a magic that has to happen to make this work. We're squaring this circle to refer to geometry for just a minute. There's a magical technique that's happening here, and it's easy to gloss over that. So for right now, we're going to set it aside, and I want you to just assume that this code could work, even though there's more to it. I want you to assume this code could work, and let me explain how it would work. And by the way, I think it's actually important to understand this plumbing, because I want you to reason about it correctly. And if you don't understand the plumbing, you'll likely reason about it totally incorrectly. So what's happening here is when I call the getData function, ignore yield for just a moment, when I call the getData function, it's still going to return to me a promise. The good news is that that promise is exactly like the promises in the other one. It has all the trustability and all those other great things about it. But I don't have to take the negative part of promises, which is all that ugly .then, .catch, weird error handling junk. I can just basically ignore most of that. And then introduces this notion of a generator with the yield keyword. You see the star up there. I like to label that as a caveat emptor, because there is a caveat here in that the generator by itself can't actually do this magic. It needs some help. But the part that the generator can do, the great part about what the generator can do, is that yield keyword allows the generator to pause. But only the generator pauses, not the entire program. So we have a localized blocking inside of this code, and that localized blocking is the magic silver bullet that allows us to write synchronous looking code that under the covers will actually function asynchronously. So what's happening here is that we are getting a promise back from the getData function on line 2. We are yielding that promise out from the generator. And the generator, when yielding out a value, it says, I'm just going to wait until somebody resumes me. And in fact, what I'm waiting is I'm waiting for a value to come back. We can see what value we're waiting for because we want to take whatever comes back and assign it to the data variable in line 2. So I'm yielding out a promise, and I'm saying somebody else listen to that promise, and whenever it finishes, give me its completion value back, and I will assign it to the data variable in line 2. Magically, our internal generator looks like it's blocking, it looks like it's synchronous, and in fact it has synchronous blocking semantics, but under the covers what's happening in the rest of our JavaScript program is all still exactly the same. It all still functions by all the same rules of asynchrony and concurrency that we know. So in other words, what we've done is we've taken the most complex part of this program, the asynchrony, and completely hidden it away. We've factored it out as an unimportant implementation detail. And we've allowed our code to return to something that is very straightforward, very sequential to reason about. I can say step 1 is line 2, step 2 is line 3, step 3 is line 4, and I don't have to worry about all of those plumbing details. Those can be hidden under the covers. That's what's so great about the generator, but as I said, the caveat is that the generator can't do it by itself. It actually needs to have a function that runs it. Some piece of code needs to understand that whole receive a promise, wait for it, resume, receive a promise, wait for it, resume. That whole cycle needs to be driven by something. And it's not terribly complex code. In one of my You Don't Know JS books, I wrote out about a 25-line version of this run function, kind of bare bones implementation. It's not terribly complex to reason about. Essentially, when you start up a generator and you get back a promise, just wait for the promise and then resume. It's not that difficult, but you don't want to write that code yourself. The good news is that a bunch of libraries have written those runners for you. So if you've used Q or Co or any of a half dozen other popular libraries out there, they all have some notion of this runner. So the magic part, again, is completely hidden. It's behind a little library, which is unfortunate, but it's not that bad, this little library runner utility, and then you pass your generator in, and that's the part that we don't have to care about, and the part that we write all day, every day, the thing that we reason about, and the thing that makes our jobs more effective is we reason about lines 2, 3, and 4 in a very sequential, synchronous-looking way. That plus the trustability of promises really does, in my opinion, significantly address the major shortcomings of callback hell. So that represents what I would consider to be kind of the bare bones basic competency that all developers in JavaScript need to get to now, is to understand how this generator plus promises pattern addresses the shortcomings of callback hell that have plagued a lot of our code. This is how I write all my code now. I write with synchronous sequential looking fashions. I let promises handle the trustability. I had all that other plumbing under the covers, and I reason about things in a very easy way, very natural way on lines 2, 3, and 4. Now, I do need to say a word about this particular pattern, this pattern of generator plus promises, because it is so important to the future of the language that they are going to be adding specific syntax to handle this idea of yielding out a promise and resuming with its value. And that new syntax actually comes by way by inspiration from some other languages. So some of you may have heard of async functions and the await utility. So async await is a new feature. It's virtually certain to be coming in the next version of JavaScript at this point. And you'll notice that I don't need an outer running utility to handle this particular code. The outer running utility has been removed because JavaScript handles it for us. Apologize. JavaScript handles it for us, which is fantastic. That's really good news for us in that we can get rid of some of the craziness of libraries, and we don't need to pick between different libraries because it's just going to be built into the JavaScript engine. But there are some caveats here. A lot of people have been acting like the async function, the async await, is like the greatest thing since sliced bread, and that it's just syntactic sugar over the run utility with generator and promises, and that there's no side effects whatsoever, and that's entirely not true. They are certainly a nicer, cleaner looking sugar. Getting rid of the run utility is nice, but it comes at a cost, and one of the costs is, for example, from the outside, this utility that I've created is no longer controllable from the outside. When I had a generator with promises and I had a runner, I had a way to interrupt that if I wanted to stop it early because I didn't need for it to finish its work. When you create an asynchronous function, it's like a black box and you have no control from the outside if you want to stop it halfway through what it's working on. And you have to go to a whole lot more engineering work to try to architect things like that. So there are definitely some drawbacks to the asynchronous function, but it certainly also has its benefits. I would encourage you not to just get drunk on the sugar and the syntax that's being dripped on here, and understand first that whole generator, promise, yield, resume thing. And once you have that cycle clean in your head, you can responsibly use asynchronous functions when they're appropriate and use generators with a runner when that is something that will be more powerful for you. Okay, one last note on the topic of generator before we kind of move on to some higher order patterns. When I was implementing this whole generator promise pattern in my own library, which I'll talk about a little bit later, I got to wondering what would happen if I had more than one generator at the same time? And what if those generators were sort of pausing and resuming and kind of transferring information back and forth? Imagine like two kids talking on a walkie-talkie, and when one kid says something, the other one's listening, and then when he says something, the other one's listening. I wondered what that would be like, and so I went to implementing that sort of functionality into my library, and the early versions of that did not look all that great. But I got a lot better at that over time, and that's actually the big substance of this talk. So we'll be coming back to this idea of multiple generators, but I wonder what would happen if I was running generator 1 and generator 2 at the same time, or in fact, what if I was running them in tandem so that they were kind of trading back and forth and they could message each other? What would that look like? How would I be modeling my programs differently if I put part of my program into one generator and part of the other, and they sort of interacted through a clean semantic? And how would that change things? And that's actually been one of the most vibrant areas of my research and development over the last year or two, has been trying to figure out what that means for asynchronous programming. So you can see we've moved from just beyond the localized semantics inside of one generator and what makes that good and what makes that nice. We're building upon that and now saying, how do I decompose my entire program into different chunks that I would model in different generators and allow those to interact in reasonable ways? So that's the area that I've been researching. But before we get to exploring that more, I need to take a side note, because there's been a lot of excitement these days around a topic called reactive programming. And this comes to us when we start to realize that a promise is by itself fundamentally incapable of handling the notion of multiple values coming in, especially multiple values over time. And if we think about a stream of values over time, we can model that in our heads as an event stream. So you can imagine if you had stock updates coming from the server and they were coming 1 per second, you can't create a promise that represents every single stock, because then you would have to be recreating a new promise every single time, because the promise can only be resolved once, and you're going to get multiple values. So we needed a pattern for almost spreading out promises over time, or for automatically instantiating promises for each value in an event stream, if you like to think of it that way. And that pattern is what leads us to this idea of reactive programming. So let me motivate that. Here I'm trying to create a promise and have it resolved whenever I click on a particular button and it has a particular class name in it. As you see on line 5, I call the resolve of my promise here, or otherwise I reject the promise. And then down on line 13, I'm waiting to see whether or not that person has clicked on it. Well, great, so now I have a promise that represents an event, and I know how to work with promises, and I know how to put my promises into generators, and great, I'm just off to the races. But the problem here is that this particular system isn't going to work, since the promise can only be resolved once. So the first time we click on the button, everything's going to work great, and the second time we click on the button, it's going to completely ignore what we clicked on, because that promise has already been resolved. So we can't actually model it in this particular way. Now we can invert it. We could say every time the event fires, we could create a whole new promise. So instead of having one promise, we have multiple promises. So now I'm going to create a new promise every time the event fires. But really, this actually begs the question, why would we even, it brings up the question, why would we even do that? Because actually, we're having to respond to the promise locally inside of that block. We're having to declare the response to our event in the same place that we declare the listening to the event, which is not a good, clean separation of concerns. We'd like to be able to declare in one part of our code that we're listening for an event, and in another part of our code a reason about how we respond to that event. And we don't have that separation anymore like we did in the previous slide. It's all tangled up together. So actually the promise doesn't bias anything here. We could just create a synchronous stream, which is what I'm showing here. I could just throw the event into an array and then start doing array-like sorts of things on it, like maps and reduces and filters and even for each, for example, because there's no asynchronicity involved. The asynchronous part has already happened because the event is already fired. So all of these are ways to kind of illustrate what's fundamentally missing and why we need a new primitive, something to grow on top of this. And that new primitive that we're most likely getting, most people refer to this as an observable. An observable is a way to model the fact that values are going to come over time, kind of like a lazy array. If we had the entire array available to us, we could just map over it. But what if we know that that array is just, that event stream is just going to continue to get data over time, and every time a new piece of data comes in, just pretend like that's been added to the list and we just do the actions again. So it's kind of like taking our normal array operations that we think of in finite lists and extending them to infinitely extendable lists over a period of time. Another way of thinking about reactive programming or about observables, which actually I find to be a really useful metaphor, is this notion of a spreadsheet. If we set up a spreadsheet and we were to say that cell B2 is, and we typed in a value like 10, and then we said C12 is whatever is in B2 multiplied by 3. Well, now C12 is going to currently have the value 36 because that's 12 times 3. But as soon as I go and change the value in B2 and I change it to 13, now immediately there's, or pseudo-immediately, there's going to be a propagation of that new piece of information, and the cell C12 is going to recalculate itself, and now it's going to display 39 instead of 36. Now what if we strung several of those calculations together? What if C12 was whatever was in B2 times 3, and then we said D9 was whatever was in C12 plus 8? Okay, so I start out with 12 in B2, and then C12 has 36, and then D9 is 36 plus 8, which is 44. Well, as soon as I change it from 12 to 13, now we go 13 in B2, and C12 has 39, and now immediately again that value continues to propagate along this calculation chain such that D9 would now show would now show 47. So if you think about that chain of those calculations as kind of like a chain of event responses, you can think about the flow of data through that calculation chain very similarly conceptually to how we think about the flow of data through an event chain that we're responding to. And that's kind of one of the best metaphors that I've come across for helping to understand what an observable is. It's representing a set of operations to a value over time as that value comes in through a stream. So there's several libraries out there that implement the observables pattern. One of the biggest and most well-known is the RX library. RX has been ported to a whole bunch of different libraries, including JavaScript. So in JavaScript it's called RxJS. And here I'm illustrating a little bit about the observable. You'll notice that line 1 and line 3 are separatable. Line 1 is where I'm setting up that I want to listen to an event. Here I want to listen to the click event on a button, and they've provided a utility with their library called from event that does that for us. We could make our own from event, and it's not that complicated, but they're providing that utility for us so that we can just get an observable. Now that observable tells us that we can that it will fire off a response every time it receives a new piece of data. So every time we click on the button in question, the observable is going to observe that and be able to respond to it. Now we're in a sense kind of subscribing to that value update by chaining off of our observable. So here on line 3, we start to create a chain, which looks a little bit like a promise chain, but it's really not a promise chain. It's really kind of like a template for what we want to have happen. Every time a new piece of data comes along, we want for the following steps to happen. So we're going to map, and then we're going to filter, and so on and so forth. And .subscribe is just their way of basically saying kind of like a for each, but I want this to fire every time there's a new piece of data. It's kind of like where you might put your console.log, for example. So that's interesting. We can, like I said, this is now an observable is mapping this concept to an infinitely extending list over time instead of a finite list that we have all together. But there's something even more interesting here, which is that you can have steps in this observation chain which themselves are asynchronous. Here I'm using a method called distinct until change. So what it's basically saying is I'm going to keep track of some state over time, and I'm only going to fire off the .subscribe. I'm only going to fire off some more data or recalculate some new data to propagate through the spreadsheet. For line 11 to observe that, I'm only going to propagate that along when the value that's come along is different than it was right before it. So if I get a whole string of 2s, for example, coming along, I'm only going to fire for the first one, and then let the next ones just sort of go by the wayside. And then when I see a 3, well, that's distinct, it's different, so now I've switched to 3, and I'll let a whole bunch of 3s come along. And if I see a 2 now, well, now we're back to throwing out an event for the 2 because that's different than the 3s that I've been seeing. So in other words, this chain itself can have some notions of statefulness and asynchronicity built into it. The point is that the declarative nature of this code means that on line 3 we can say, this is all the stuff that I want to have happen. So this is like setting up our spreadsheet with all those different chained calculations. And that can be separatable from line 1 where we actually attach it to some source of data. There's a fantastic website out there called rxmarbles.com. If you haven't checked this out, I highly recommend you do. I think you can probably learn like 50% of reactive programming just by playing around with rxmarbles.com. It's a really fantastic site. You can take these little bubbles and move them around, and when you move them to different locations in their relative sequence, you see different things. So here we see the distinct until changed being visually shown, where we have the top arrow line is the stream of data, and the bottom one is the response stream that's coming out of the distinct until changed. It's creating a new stream with a new set of data in it. And you'll notice that when the first pink one comes along, it fires it onto the response stream. When the pink-orange 2 comes along, it fires it. When that blue 2 comes along, that's a duplicate. That's not distinct, so that one gets dropped. It's not on the response stream. When we get a 1, well, hey, that's different than the 2 that I just had, so we fire the 1. And then when we get a 3, that's different than the 1 I just saw, so we fire the 3. So we can model this as basically a stream transformation. If there's a stream of data on the top, we're applying a set of practical and straightforward rules to determine what the response stream should be. That's very similar to the calculations that we set up that are chained together in a spreadsheet. Now, Rx is a fantastic library. RxJS is a fantastic library, but it's really big. They have done a lot of work lately to modularize it, to let you pick a lot of tiny little pieces and things like that. But the documentation is, quite frankly, very intimidating, I find. Even with my understanding of the actual concepts from rxmarbles.com, trying to read through the API documentation, you've got to come with a lot of energy because there's a lot to wade through. It's a big library. It has a lot of capability to it. Big thumbs up to all the stuff that they've invented there. It's fantastic, but it can be very intimidating, especially for an early learner. So now I want to point out, I mentioned earlier that I have a library called the word async plus the word sequence smushed together, mostly because there just aren't any other good words for GitHub projects anymore, or npm sequence and projects. But Asequence has been around for 4 or 5 years now, long before reactive sequences. The goal has always been to create a very tiny library that incorporates the best 80% parts of each of the major asynchronous patterns and presents them in a way that is very simple to understand and quick to learn. So it tries to remove some of the complex corner cases and other weird things that you might stumble across and create just a very simple way of dealing with asynchronous abstractions. So Asequence has support for promises, it has support for generators and the runner pattern, async functions, but it also has support for this notion of an observable or reactive programming, and in the asynchronous world I call that a reactive sequence. So just as a quick glimpse at that, you're going to notice that it's going to look very similar to what I was just showing you. If I made a from event utility, if I wanted to make my own, this is one of the possible ways to create that. And you notice the asynchronous library here on line 2, and I'm making a reactive sequence. And the way I make that reactive sequence is you can see that every time the button gets clicked, or whatever the event type is, every time it's going to get that event fired, it's going to call the proceed function, which is going to fire off a response to that reactive sequence. So lines 1 through 8 represent the similar to what we saw in the previous couple of slides ago. They represent the creation or subscribing to an event source, creating an observable, if you will. In this case, I call it RSQ because I call them reactive sequences. Lines 10 through 21 represent a completely separate way, or a completely separate part of the program, which is subscribing to that or responding to data that comes along that reactive sequence. So here I have a normal chain, just like I have in asynchronous, and this chain can have promise steps in it, it can have generator steps in it, it can have CSP steps in it, have whatever you want, but it's going to work conceptually very similar to the ideas that you have with the maps and filters and reduces. So you can see it's a library that tries to take the best parts of those worlds and slim them down to something a little bit easier to manage mentally. The most important thing about reactive programming is this notion of streams being composed together. That's how you model the complex actions that are happening in your programs. So that support also exists in asynchronous. So here, if I have a stream called RSQ1 and another one called RSQ2, if I wanted to create another event stream, RSQ3, that represented when I had received an event from both of those, in other words, if I've only ever received clicks and not key presses, we don't want RSQ3 to send anything out. That one is called .all. And I could create asq.react.all is a stream operator. It takes 2 or more streams and it creates a third stream, or it creates a response stream that is the response with those rules applied to it. So RSQ3 is the .all operator. RSQ4 is the .any operator. And to visualize the difference between those, I'm going to show you those names mapped to what they map to in the React world. In the reactive, the RX world. So in the RX world, the all is called zip, and you can use that same name in my library if you prefer zip. I think zip is a weird method name, so I like to use all. But you can see here exactly what zip does, or exactly what all does. It waits until it receives both a 1 and an A, and then it fires a composed element, a composed event with both pieces of data in it. Then it waits for a 2 and a B, and it fires a composed event. And you notice when it gets C, it did not have one from the other stream, from the upper stream, so it can't fire anything yet. And when it receives the 3, then you get a 3C. That D is just stuck in a buffer waiting until 4 comes around, and so on and so forth. So the all or the zip is saying I need to wait for all the input streams to have a piece of data for me to operate on before I compose them together and put something on the output stream. Well, the other stream operation that I talked about, I called it any. That's referred to as merge in the RX world. You can use that method name, merge or any, either one of those will work. But you'll notice here that I'm firing an event on the response stream anytime I get a piece of data from either of the input streams. So I get a 20, a 40, a 60. As soon as I get a 1, I get that one out, and then 80 and 100. The event datas are not composing together. They're actually just being fired individually on the merge stream. So I model a program differently with the merge operation than I do with the zip operation. And there are about 50 or 100 other sorts of operations like that in the RX world that you can learn and play around with on RX Marbles. I have taken 5 or 6 of the most important of those, I think, and put them into asynchronous. To illustrate all of these different things and how they're all going on, I want to point you to a project that I put out a couple of months ago called A Tale of Three Lists. I like to refer to this as basically the to-do MVC project, but for asynchronous programming. I created a simple little utility kind of demo of various different asynchronous actions happening. These are events firing at different speeds and being subscribed to at different throttled speeds. And UI events like you clicking on things and pausing and resuming and so forth. All these different things are all happening at the same time, and there's a lot of different ways for you to model that in your code. And what I observed was it would be useful from a learning perspective if we had one code base implemented in each of the different major asynchronous patterns. And so that's what I did. I've re-implemented this exact same demo with the exact same behavior 7 different times. So the first time with callbacks, and then another time with promises, and another time with generators, and another time with reactive sequences, and so on and so on. So you actually have the exact same code base side by side implemented with different abstractions, and you can look at those pieces of code side by side and start to get an idea of the relative strengths and weaknesses of each of the patterns. There'll be places in that code where you look at the callbacks and you're like, oh, that's terrible compared to the promises. But quite frankly, there'll be places where you look at this pattern, reactive programming, and you're like, that's a lot better than promises. And then you look at another place and you say, well, actually, promises are better here. So again, it's not to say that there's one pattern that is better than all the others, but to say that there are relative strengths and weaknesses in all these patterns, and it's helpful to have a code base to look at side by side. So I encourage you to check out a Tale of 3 lists if you'd like to look at some non-trivial, non-example code that does a little bit more heavy lifting, but it implements these different asynchronous patterns kind of side by side. Okay. So a lot of this has been build up to, and I know we've already been talking almost for an hour, but a lot of this has been build up to what I really want to talk to you about today. It's this idea that there's another way of modeling data over time. If we've been modeling it in the reactive programming way, and certainly there's a lot of attention being given to that, a lot of libraries and frameworks that are spinning up in that world. But I'm not convinced that that's the only way or even necessarily the best way for us to model our complex applications. In fact, I'm kind of convinced that eventually we're going to come around to realizing this other model has a lot of strengths to it as well. And that model, the first way to observe this is, you remember when I said that we would have multiple generators? Well, what would we do with those multiple generators? What we're going to do is model our programs as a series of channels. And possibly you can think about as promises. Promises almost become an irrelevant implementation detail at this point because we don't really see the promise front and center. It's hidden under another layer of abstraction in much the same way that in the observables RX reactive programming world, we don't really see much of the promises that are under the cover. So here the promises are going to exist, but they're kind of hidden away. So what is a channel? And what is channel-based concurrency? Well, I could invent this myself, and that's when I said earlier, I started trying to invent that a couple of years ago when I was doing multiple generators together. I was trying to invent something like that. And then I realized actually several smarter people than me have already invented it. And it goes by the name CSP, which you might think of as content security policy. That's what most Google search results will give you, but it's not that. It's an unfortunate overlap in acronyms here. We're referring to CSP, which means Communicating Sequential Processes. So CSP is a model that comes to us from a paper, a book that was written back in, I think, the 1970s, a long time ago, of that same name. It's a model for managing concurrency, and it uses channels to model the interactions between independent pieces. So we're going to look at that, and we're going to look at how that can be ported into JavaScript, how that has been ported into JavaScript. But just so you know, CSP is the model for concurrency in the Go programming language, and also the model that's used in the ClojureScript library through their core .async module. They use the CSP module, the CSP model. So this isn't something I've invented. It's not entirely obscure. There are some really smart folks that are fully committed and believe that this is the most effective model. If you've seen or heard anything from either of these two gentlemen, you'll know that I'm referring to some very, very smart and very, very forward-thinking individuals. So Swanadet, David Nolan, I read everything that he's ever written and only understand about 10% of it, but he is fantastic, kind of leading the way. I always think that he's about 1.5 to 2 years ahead of all the rest of us in terms of where JavaScript is headed and where programming in general is headed. He is a major figure in the ClojureScript community. And James Long, Jay Longster, he's also fantastic. He's done quite a bit of work to bring that CSP semantics into JavaScript. He was one of the first libraries that I saw doing that. So if I'm standing, if I'm doing anything, it's because I'm standing on the shoulders of those giants, or really rather just clinging on for dear life. So they're fantastic. Check out the stuff they've done. So let's very quickly kind of try to illustrate what this means. If I created an object, here I'm instantiating it using some method called chan for creating a channel. It's called ch. Now, what is a channel? Conceptually, you can think of a channel kind of like a pipe, if you know what pipes are in the node world, for example, except that a channel by default can only have a single message transmitted across it. It has no buffer, or it has a buffer size of 1, if you will, which means if I try to put something into the channel on the right end of it, like I could with a pipe, if I can't actually fully put that message into the channel until there's somebody else that's already ready to receive it. Or vice versa, if I want to receive a message from a channel, I can't receive a message unless, of course, there's one waiting to be sent to me. So if I had two independent pieces in my program, these two independent generators that we see here, they're oftentimes now referred to in this model as coroutines, or rather Go routines, since we're being inspired heavily by Go here. These two different Go routines represent two independent parts of my program that otherwise would operate entirely independently. And by independently, I mean the only dependence whatsoever is that JavaScript is single-threaded. Otherwise, they don't share any memory or do anything. They're just dealing with two different parts of my program. But if I wanted for them to be able to coordinate at some point, and I wanted to figure out how would I model that coordination. You remember, I've said all along this entire talk that this is all about coordination. How would I model that coordination? Well, it turns out the channel is actually a really nice, beautiful way of thinking about that, because the channel has built into it a blocking semantic. When it only has a buffer size of 1, it means that I can't finish sending the message until somebody else receives it. So if the one message wanted to send a message over to the to utility, or the to Go routine, it would say put, and you try to put the message 42 onto the ch channel. You notice I'm using a yield there because I want to locally pause while I'm attempting to put that message. I don't want to go on. I want to pause while I'm attempting to put that message. That gives me the blocking semantic. Now, on the other part of the world, inside of the to Go routine, I am waiting to receive it, and I'm doing a yield on a take action. So I'm saying yield csp.take from that channel, and the most important thing to understand here is that it does not matter which one of these two lines, line 3 or line 8, it doesn't matter which one of them happens first. We don't care. It doesn't matter, because yielding on a take before there's a message is the same thing as yielding on a put before there's a taker. We just simply wait until somebody matches up on the channel, and then the message is transferred, and then both of us are unblocked at the exact same moment, and we continue on about our independent ways. So the one utility, the one Go routine here from line number 1, is able to operate completely independently until it needs to coordinate with somebody else, and then it simply does a blocking channel operation, a put or a take. And 2, the Go routine, is also able to do the same until it needs to communicate with someone else, and it uses the channel to do that. There really is no more complexity necessary to understand the concept of CSP than that, this notion of blocking puts and blocking takes. And it really transforms the way that we model our code. I wish there was some magic example that I could show you that would just convince all of you simultaneously that this is amazing, but it's a slow burn. When I first saw it, it was kind of intriguing, but I didn't really understand how I would use it. And it's taken quite a while to play with this in my code and get my head out of the other models and the other patterns to think about it this way. But the more I've played with this semantic of modeling things through blocking puts and takes, the more I think that it has significantly increased the readability, the understandability, the maintainability of my code. So I think there's really something here to this CSP model. And I think it's telling that people like David Nolan that are all in the ClojureScript world, they've written incredibly sophisticated but not even that long, not even that big, but sophisticated libraries like the OM library. It's all built on this idea of the CSP model for managing concurrency. So, as I said before, he's always a couple of years ahead of the rest of us. Since he's doing this stuff right now, I think we'll probably be doing more CSP in a year or two, and I'm just trying to be on the leading edge of that to try to understand how to do it better for my code. So I encourage you, if any of this is at all intriguing, to kind of play around with it. And as I said, with a tale of a tale of three lists, there's an implementation in there of that code base using CSP semantics. So this is a quick little snippet of that. It just shows you I'm doing a yield ac.take there. So I'm taking from a channel called feed restart, and then I'm taking from another channel, which is basically just a timeout delay, and then I'm yielding to take from the new item feed, and I can yield on a put and so forth. So if you're interested in seeing that implemented in a more sophisticated non-demo way, you might check out more of this code base, look at the CSP implementation of the three lists demo. So hopefully that's at least intrigued some of you that CSP is amazing. I'm pretty convinced that CSP is at least going to come alongside the amazing stuff that we're doing with reactive programming. If not, start to overtake some of the excitement in there and shift the direction more in the CSP world. That's not to say that reactive programming sucks. I think it's amazing. That's why it's in my library. But I think there are things that reactive programming does well that are great, and then I think there are some things that CSP is better at. And in particular, the thing that I have found to be most useful about the CSP world is this idea that the channel has the built-in capability to do back pressure. The idea to signal from the subscriber back to the publisher that we don't want any more data right now. That's built into the semantic of the channels. And if you want to do that in the reactive programming world, you kind of have to get into some more complex stuff like hot versus cold observables and converting between the two, or having two observables go in the opposite directions and have a back channel to send that information. So it's possible, but I find that to be my attempts at that have been much more complex, and it just falls out almost by accident. It's just built into the way we think when we deal in the CSP world. So there are some things that are actually been very enlightening as I've tried out more of CSP. So a full more than an hour into this talk, and I still haven't explained to you whatsoever why the talk is called Blocking Across the Wire. So what does that mean? What do I mean blocking across the wire? I got to thinking a while back that if I could block across coroutines within the same JavaScript program, couldn't I also block across channel communications where the two coroutines were not local to each other? Maybe one coroutine is in my JavaScript in my browser, and another one is in a web worker, and another one's on a server, and another one's on an entirely different server. The blocking semantic doesn't care what the channel is connected to. It's a simple way of modeling the interactions between these pieces that it's completely agnostic of where those pieces actually reside. So, for example, what if I could write some code like that on the server that's trying to put the message 42 onto the channel, and then another piece, and that happened to be in the client, and I wanted to take a message from that channel. So that's a server pushing a message up to the client, but it turns out that it actually could be completely reversed, and the code would not change whatsoever. This code is exactly the same regardless of where the code is running. That's an amazingly powerful thing, to be able to abstract away the environment from the pattern. And that is one of the things that I'm most excited about with CSP, is the fact that we might potentially be able to do that. To make this happen, to be able to bridge across the wire, we would need a channel that was capable of, under the covers, handling all the complexities of asynchronous messaging across, for example, the network, or across inter-process communication between two child processes or whatever. We'd need something to do that. That's not built into the standard CSP libraries. But I got to wondering, how hard would that be? And on this conceptual surface, I thought, oh, this won't be hard at all. I'll just make a channel that's got like a WebSocket underneath it, and whenever I try to take from the channel, I'll send a message and send a message back. And it turns out it was a lot more complicated than that. It took me 6 months of fiddling around trying to figure out how to get even a proof of concept demo of this, but I've built a thing called Remote Channel. And it's designed to basically be a channel that drops into an existing CSP code base, and the way you instantiate the channel, it automatically knows that it's connected over the wire, but the code that uses the channel doesn't know and doesn't care. So I have normal channels that are just local, and then I can have other remote channels that look the same, but they have this special capability that they're bridged across a network wire, for example, and my code base just consumes and takes from that channel without worrying about it. The other challenge here is that I did not want for this remote channel project to be only tied to my library, to Asynchronous. So I built it so that it is agnostic, and that is actually super challenging to do because there are differences between the libraries. But the goal of this is that it doesn't require asynchronous. You hopefully could use this same utility using one of the other CSP libraries that is out there to bridge across the gap. So I'm not going to get into too much of the details of how the library works, but you can imagine the gory guts of trying to do handshaking of messages back and forth and connections and things like that. It's definitely complex. What I do want to spend a few minutes looking at, though, is just illustrating what some of that code looks like. All of this code that I'm showing you right now is up on the remote channel GitHub library, so it's in the examples directory. I'm just literally showing you the files that are already there. But this is an example where I have a server, so this is code that would run in Node, and you can see that because it's obviously doing Node things like listening on port 8005, for example. But the important part here, as we see like on line 13, this is I'm initializing my CSP my remote CSP channel library with the CSP that I'm currently using. So here's where I'm providing my namespace. I'm providing it asynchronous. You ideally should be able to provide it any CSP library's namespace in that particular position. I'm using asynchronous since that's the one I built. And then you need to additionally tell it what method it needs to call to build normal channels. So I'm telling it there. And then if your particular implementation of CSP doesn't use promises, then you need to provide a wrapper for throwing out promises. And that's what I'm doing with asynchronous. If yours already uses promises, you don't even need that adapter. Okay, so that's just like a single call that we make to initialize the library so that it kind of knows how to latch itself on to your CSP implementation. And then let's look at using it. So down here, this is my asynchronous stuff for doing CSP. I want to spin up a server socket. So this is a method that I've got declared. I'll show you in a moment. But I'm going to get back a channel that I can just take from. And so spinning up the server socket is actually going to do some socket I/O work. If you've ever worked with socket I/O, this is what's happening here. I'm doing a socket I/O connection, and whenever I get that socket back, I am attaching it. So here's where the magic kind of happens. Whenever I receive the socket back from socket I/O, I get some IDs so that we know we're talking uniquely to the same channel. I send those across, and the important part here is that I define my socket I/O transport. So that's the second step. The first step is initting the CSP. Second step is defining the transport. And then after all that ugly plumbing is done, and I know that's a little bit complex, but after all that ugly plumbing is done, then all we need to do to get a channel is call the open channel method. And under the covers, it's automatically going to bridge across and look for somebody else on the other side having gone through the exact same steps. And if they provide the exact same IDs, then those channels will be open and connected to each other. And now we have a channel here that I can simply use exactly the same way I use any other channel. So down here, my server is going to calculate the Fibonacci number. and send it back. So a small Fibonacci is not going to take long, but I'm going to let the server block while it's calculating Fibonacci and then simply push it back up to the client. So here's my put, the matching of that up here in the client. This is the JavaScript that I load into a web browser. You notice I'm doing the same thing. I'm initting my CSP, I'm defining my transport, and now my get fib is saying, I want you to calculate Fibonacci of 42, and I'm simply going to wait for you to finish. So I don't care where that is. That could be, as I said, this particular one is connecting over socket IO, but this could be connecting over Ajax, or it could be connecting to a web worker, it could be connecting just about anywhere. So hopefully that helps to illustrate a little bit how this remote channel stuff could work. The nice thing about this is that this particular part of the code is exactly the same between client and server. And the looks of this code, while that might look a little bit intimidating, the looks of this code are basically the same semantics in both places. So you could probably wrap that into a little library and even share the code and not even have to write it twice. Okay, so hopefully that gives you a quick illustration of where I'm going with that. This is super early alpha work, but my goal is to be able to use CSP across the connection boundary, if you will, so that it doesn't matter where it is. So one last thing that I want to share with you as we start to wrap up, and hopefully I'll have a few minutes for some questions here at the end. One last thing I want to share with you is that I mentioned before at the beginning of our talk today that we were dealing with a thread in JavaScript. And there's some good parts about that, but there's some bad parts about it, frankly. There are some really high performance applications that really genuinely need multiple threads. And if you work in the node world much, you know that they have child processes and lightweight threads and fibers and about a half dozen other things people have invented to try to be able to give multi-threading capabilities to a JavaScript environment. A lot of those have some fairly complex things that that require you to wrap your brain around programming semantics that you probably aren't familiar with unless you've done threaded programming in other languages before, you know, mutexes and semaphores and other sorts of blocking things. So I got to wondering, well, if I can remote across the network boundary, that means I can actually remote across the thread boundary as well and have exactly the same simple blocking puts and takes method. So what if we just blocked across all the threads? What if we could spin up lightweight threads using any of a variety of those mechanisms that are available, like in the node world, for example? What if we could spin up multiple threads, or if we're in the browser, we can spin up multiple web workers and distribute work across the web workers, but not have to have complex mechanisms for that coordination? Well, if we can remote across a network boundary, we can remote across a thread boundary as well. So yes, actually what I'm saying is multi-threading in JavaScript, and a really simple way of doing that, which doesn't require you to learn anything more than blocking puts and takes. And CSP can do that. So we think about all the boundaries that we might want to cross. We've got a browser to a web worker. We've got one browser instance to another browser instance. Maybe like the main page to the iframe, for example. We've got a browser to server. We've got a server to a child process. We've got child processes to child threads, and the list goes on and on. All of those basically thread boundaries, if you will, for distributing work out, we can model those exact same interactions with the CSP semantic. So as a quick illustration of that, another example that's included in that remote channel is doing exactly that. So here I've got, this is the code that runs in the client. You notice that I'm initializing the CSP, and I'm going to define a transport down here, and my transport that I want to define is for web workers. So I actually want to communicate from my main page to a web worker using the blocking CSP semantics. So here I define my transport, and this is going to allow me to, so if I scroll down here, this is how we're going to be able to listen to the web worker. We have we construct our channel, as I said before. We call open channel to get our channel, and we take from that channel. So we're just going to ask for a piece of information from that channel, and as soon as I receive it, then the message is received. So now I have this web worker. You remember up here I was creating a worker instance, and that worker instance is pulling up this JavaScript file. So let's look at that JavaScript file. Well, again, it has the exact same thing. I initialize my CSP, I define a transport, and then I create myself a channel. So those three steps are kind of repeated over and over, and it's right for somebody to put that into a simple little framework and do that for you. But once I have that channel opened between worker and browser, my semantic is no more complex than putting a message. Here I'm just doing something stupid like running a really long running loop and then sending the value back. But this could be much more interesting work, like sorting data, for example. All right, so that's me talking to a web worker, but at the same time I can be talking to a web worker, I can also spin up a connection to a server. So here I'm in the server, and I want to define my transport, again using socket.io. This looks the same as before. Over on the server side, again, I define a transport that listens. Let's come up here. So here's my initializing the CSP, and then down here is where I define the transport to connect over socket.io. So there's my client and server connection happening. I want to listen for it to ask me, but now I want to spin up a node child process. Well, I just need another channel for that. So I spin up a remote channel, define a transport for connecting over and standard out to a child process, and I'm on my way. And here I have normal puts and takes, just like I always would. Over in the child process, totally unsurprisingly, we have the exact same thing happening again, initializing the CSP, defining the transport to connect, and then simply doing puts and takes. So hopefully what I'm illustrating here is that we're doing some pretty complex stuff. We're making communications between processes and web workers and servers and threads and all kinds of other things. But what it really comes down to is the simplicity of understanding that concept of puts and takes. And if you can wrap your brain around that, you can actually do some pretty powerful, even multi-threaded processing without too much complexity. This is the stuff that I'm excited about these days. It's kind of the future. I think this is where JavaScript's headed, or at least something like this. And I don't claim to have invented it by any means, but I hope I'm pointing some other smarter people at it so that we get lots more eyes and ears trained on this problem. And I think we're going to see some amazing stuff come out of the next couple of years. Bottom line, CSP really is a powerful, simple pattern, and it's designed for distributed, coordinated concurrency. And it does that job pretty well, I think. So that's what I've got to talk about today. I hope that this was interesting. I hope that it was instructive to you. I hope that it's opened some of your eyes to look into some stuff. We have about 10 minutes left, so I'm going to stop the presentation and kind of switch back over to question mode. And I think the moderator will step in and help us go through some of these questions. The first one I see mentioned here is there is an unfortunate confusion between CSP and CPS. CSP is communicating sequential processes. CPS is continuation passing style. It's very unfortunate that they're closely related but actually entirely different. So yeah, that's unfortunate, but that's what we've got. There were a couple of questions, it looks like, about Maker Square. One of them is Maker Square. Yes, Maker Square is part of the network partner network of schools under Hack Reactor. So that was the question there. The slides will be available for download. Yep, I will have the slides out, so we'll communicate that out, but I'll put these slides up as I always do. All right. This question says, is this behavior more like a monad? I'm guessing by the sequence of questions this was probably somewhere related to promises. And yes, promises are closely related to monads, but I'm not going to go any deeper in my answer than that for two reasons. First of all, because we'll get way deep in the weeds, and second of all, because I am not qualified to really fully talk about them. Smarter people than me have observed that there are some close similarities between promises and monads, but I won't go any further than that. All right, so let's see. Do you mean that with async you cannot break out due to an error in getting data? Yeah. So that's the async await functions, I imagine. No, I'm not saying that an async function cannot stop itself prematurely. If it had a network error, for example, and couldn't finish downloading some data, it can stop itself. What I'm saying is that from the outside, you cannot stop it. So, for example, if you have an async function that represents a network request that's downloading a bunch of data from the server into the browser, and for some reason, whatever in your application, the user doesn't want to keep going. Maybe something's happened in the app and you want to cancel that. You cannot cancel what's happening inside of the async function from the outside of the async function. So if you want to make the async function do some sort of cancellation, you're going to have to independently architect some sort of mechanism like that, like setting a shared closure variable flag that you set to false, and it checks it every so often. If it sees the variable, then it cancels itself. You can't directly signal that from the outside. With generators, you can, because generators can either be resumed successfully with a .next, or they can be, you can throw an error into them using .throw, or you can simply abort a generator right in its mid-process by calling .return. So generators afford us more control from the outside, and I find a lot of times in my programming that I want that control. I need that control. And so that's why I'm not as excited about async functions preventing you from doing that. So hopefully that explains that. Can you quickly explain the purpose of wrapping the generator in a run function? Yes. The generator we did not show in the code. Let me see if I can quickly slide back up to the slide that this was talking about. This generator code here, we did not talk about in this generator code. We're not seeing the fact that to run a generator means creating an iterator and calling .next on it over and over and over again. There's plumbing work related to running this generator. It's not hard, and I've written about it more. If you want to read more about it, go read the blog posts or the books that I've written. But there is plumbing work to do, and people don't like plumbing usually. Usually they want the plumbing to be hidden away underneath a nice cabinet or something. So that plumbing work is done by the run function. Basically, that cycle is that you call it.next to start a generator, and when you get it back, you get a promise that it's yielded. You need to listen to that promise until that promise resolves, and if it resolves as a fulfillment, as a success, then you want to take the value that it resolved with and resume the generator by calling .next again and passing the value in. If instead the promise was a rejection, then you want to throw that error into the generator. We didn't go over this, but generators, because they have synchronous syntax, you can also have synchronous error handling across those statements. So line 3 here, for example, I could wrap a try-catch around just line 3, and if a rejection happened in the promise, that rejection would come into the generator as a thrown error that my try-catch would catch. But that plumbing to resume and receive promises and wait for them and resume and all that stuff, that's the stuff that's done by the run function. And generally speaking, that's also the stuff that's done automatically by JavaScript with async await functions. It's just that in the process of them putting syntactic sugar to automate it, they also took away some of the controls that we used to have. So, all right, there were a couple of questions about video quality, audio. Sorry if there were video and audio questions, apologies. Any URL to the original papers on CSP. If you search for, I don't have the URL here, but if you do a Google search for Hoare, it's H-O-A-R-E, that's the name of the gentleman that wrote it. Search for Hoare and CSP. You'll find his paper. I do have links to it in my various blog posts. If you found any of my blog posts on the topic of generators, watch my Twitter account because I tweet about them regularly. If you found any of those, you'll see that I have links to it in there as well. All right. What libraries are available for implementing CSP in JavaScript? The only one I found was JSCSP. That's the main one, but Asequence also. So I would say those two, JSCSP and my Asequence library, they both implement the Go-style CSP in JavaScript. I imagine there's probably a half dozen other ones that I don't know of. Maybe they're awesome and I just don't know about them. So I'm not saying those are the only ones, but those are the two I know of. JSCSP is the one that was made by James Long, who forked that from another project of the same name, so him and another guy had worked on that quite a bit. And then Asequence is the library that I built. All right, let's see. I'd love your recommendations on more resources to learn about CSP. Unfortunately, it sounds very self-serving, but the only resources I can tell you to learn about are the ones that I talked about here, which are the A Tale of Three Lists. That has a CSP code base, so you can actually see some slightly non-trivial code working with CSP and kind of get a sense of that. I have written extensively about it on my blog, so if you find my blog, it's blog.getify.com. There's a 3-part article series on concurrency, and the 3rd part of that article series is all about CSP. I've written blog posts, guest blog posts in other places, and I've mentioned it a few times in my You Don't Know JS book series. So those are the ones that I can refer you to. Other than that, when you read those, you will see that I link to the writings of people like David Nolan, Swanadet, for example. He's written a bunch of stuff early on about it, and that's what got me interested. So from my stuff, I would say immediately you should start looking at the stuff that David Nolan has written. All right, and it looks like that might have been the last question. If we miss getting to answer your, if we miss getting to answer your question for you live here on the broadcast, please just remember, let me put this final slide up. Please remember my contact information. I can be reached on Twitter or any of the other places that are listed up on the getify.me website. I would love to hear your feedback or questions. If there's anything I can do to help you along in the process of learning asynchronous programming better, I would love to do so. I would also just give a final plug. Come find me teaching at some conference or have me come teach at your company. That's what I like to do. So feel free to reach out and ask about that as well. Thanks very much for your time and for listening to me today. It's been a lot of fun.